All right, so here we're going to start looking at inverse functions. If you look at this first graph, we have two functions. The first one in red is f of x equals x plus 1. It has a slope of 1 and a y-intercept of 1, is where I got that. If we look at the blue graph, it is f of x equals x minus 1. It has that same slope of 1. It's parallel to the other one, but it intercepts at negative 1. And in fact, it turns out, and we'll dive into this a little more, that this blue graph, this blue one, is actually the inverse. And we put that little negative 1 there like that to indicate that it's an inverse of the red line. And so there's that. And then if we come over to this next one, we can see that we have two more graphs here. The red graph is f of x equals x squared, the parabola, but only for x greater than or equal to 0. And then if we go to the blue graph, it is actually f of x equals the square root of x. And if you look here, this is actually the inverse of the other graph. And the one thing you can notice that you see here, and again, it might be a little more complicated than this at times, but over here in the first graph, it's x plus 1. And how do you undo a plus 1? It's with a minus 1. And so the inverse is with a minus 1. And if we look at the second graph, it's f of x squared. And how do you undo a square? It's a square root. And so therefore, that is the inverse function. And so you can see that kind of right there. So to know if a function actually has an inverse function, it must pass, your function f must pass the horizontal line test, okay, in order to have an inverse function, okay, in order for its function to be an inverse. And basically this test is just like the vertical test. Vertical test, it was a vertical line could only intersect it once in order for it to be a function. Horizontal line test is a horizontal line intersects it at most once. So just horizontal instead of vertical. And what that will mean then, of course, it's kind of an equivalent statement, is that f is 1, 2, 1. That means that, yes, we have functions that can have two different inputs give you the same output, but one-to-one functions mean every input gives a unique output. There's no overlapping of the outputs. So in other words, if we have something like this, where this is our two inputs, and it maps over, and they both map to the same output, that's still a function. It's a function, but it's not a one-to-one function. A one-to-one function means every input maps to a unique output. All right, so this is a one-to-one function. Okay? And one more very interesting thing about the identities, another big property, is that identities, or I'm sorry, inverses here are actually, if you combine them, if you do compositions of them, you will get the identity function. So in other words, f of f inverse of x is just going to equal x. And the same thing the other way, f inverse of f of x is also just going to equal the identity function. Okay, so it equals the identity function. It'll just end up equaling x. What happens when you do these is the domain and range, they swap. They'll switch places. The domain becomes the range, and the range becomes the domain. Okay? And all the x values become the y values, and the y values become the x values, and the graph is reflected like a mirror over line y equals x. And so if I come back up here to the beginning, if I draw in y equals x, you can see that essentially it acts like a mirror. Y equals x. They're like mirror images of each other across it, and the same thing on this one. If I do a little better job of drawing it in, there it is, and the two functions look like mirror images of each other across it, like they're looking in the mirror, like you drew one of them, and then while it was wet, you folded it across that y equals x line, and then like kind of creased it down, and it made an image of itself over there, right? Like if you did it in wet paint or something like that. Okay, so that's the basic idea of some properties of some inverse functions. So some applications of this is essentially they undo each other since f inverse of f is just identity. What this means is that this is just going to equal 789. Okay? So it's just going to give you back what you put in. They undo each other, which is what inverses do to each other. So one of them might square it, and the other is going to square root it, and you get back what you put in. If a function f has an inverse, and f of -7 equals 8, then what is f inverse of 8? Well, if you think about it, if we input -7 into f and it gives us 8, and then we input 8 back into the inverse, it's going to take us back to it. So we have -7 and we have 8, and the function f takes us to 8, and then the function inverse takes us back to -7. So f inverse of 8 is just going to be -7. See, if a function f has an inverse, f inverse of 3 is 5, then what is f of 5? And in a similar fashion, f of 5 is just going to take us back to the 3. Okay? So again, they just kind of undo each other. Determine if the given function f and g are inverses of each other. All right, so in order to check if they are inverses of each other, we simply have to plug one as a composition into the other. It really doesn't matter which way you do it, and it should work out the same. So here, I'll do f of g of x, and so I'm going to plug g into f. This will be 3 times x minus 2 over 3 plus 2. And then if we distribute, or the 3 will cancel, and we'll get x minus 2 plus 2, which will just equal x. All right, and if you were to do it the other way, do g of f of x, you're going to get the same thing. It's going to turn out also to just be x. Feel free to try plugging it in and seeing, but you get the same thing. You'll get you'll end up just canceling everything out, and you'll end up with an f. So if that's true, then we can basically say that g is the inverse of f, or you could say f is the inverse of g. Either way, they are basically inverses of each other. All right, for this next one, I'm going to leave that for you to give a try to and see if it works. And I'll put the actual working out of it up on the notes after, but you go ahead and give it a try and see how you think, and then see the online notes to see what the final answer is. All right, so for E, we've got here, we can go ahead and see this one. Is this function one-to-one? Well, if you look at this is actually a semicircle. It's part of a circle. If you have the function x squared plus y squared equals a squared, that's the function of a circle. If you solve it for y, you get square root of a squared minus x squared with a plus or minus. So the plus part would be the top half of the circle, the minus part would be the bottom half of the circle. We only have the plus part here, so this is actually just a semicircle like that. And it's got a it's a squared is 9, so it has a radius of 3, so this is a radius of 3, so that's a 3, that's a 3, even this is a 3 up here. But this is a semicircle, and it completely fails the horizontal line test, right? If I draw a horizontal line here, I'm hitting it in two places. So this fails the horizontal line test. All right, and so it is not 1-to-1. Okay, fails the horizontal line test, not 1-to-1. Okay, so next page, how do we find inverse functions? Well, essentially the first thing you have to do is check to see if it's 1-to-1. So you have to check to see that if it has an actual inverse that is a function. So you check it and you see. That's step one. After that, you basically replace the f of x with a y. So, because f of x is typically just y. And then you swap x and y. You replace all your x's with y's and all your y's with x's. Go through and resolve for y. And if it has that inverse function, then you just swap out where you wrote y with the f inverse of x, like that. So let's try this one. First one is 3x minus 5. It is linear. So it is linear. It's a straight line. So it is 1-to-1. It would pass a horizontal line test. It's just a line, right? If you look at this graph, slope of 3, intercept -5, so it's going to be something like that, where this is -5 and it has a slope of 3. So it's going to look something like that, and it's going to pass. And so we start with replacing this, making this y equals 3x minus 5. Then we swap it and replace the y with an x and replace the x with a y. And now go about solving it. So add 5 to both sides and you get x plus 5 equals 3y, and divide by 3. And I'm going to also swap the sides here as well. And I'll get y equals x plus 5 over 3. And therefore, the f inverse is x plus 5 over 3. And if you wanted to check it, you could make the composite function of the two, and you should get back just y equals x. Okay? I'm going to go ahead and leave B for you to try, but I will complete it for the notes online so you can take a look to see how you're doing. And then I'm going to flip over and let's take a look over here. Here we're doing the same thing. You want to pass the horizontal line test, but here what I want you to also do is go ahead and graph it, right? Graph it and take a look at what the domain and range is of each function, so you can kind of see that they flip-flop, that the domains of f become the ranges of f inverse, and the range of f becomes the domain of f inverse. So give that a try, and don't forget to notice that if you graph them, that that you're going to end up with this line right here, this y equals x. That's going to be what it's going to reflect across when you actually do the graph. And if you want to see what these two look like worked out, then again, they'll be completed on the notes for you to go ahead and take a look at. All right, that's all.